Welcome back to another Learning Integrations episode where today we'll be focusing on trigonometric functions and we'll be finding the antiderivative using substitution or by substitution method. So I'll give our first example. Example 1. Here we have our function equals x multiplied by sine of x squared. Now, one of the rules for using substitution or steps that you would follow is, firstly, if you have a function times a function, that's yes, and is one of the inner if on one of the functions is the inner function of that, if you derive it, will you get the first function? It's a bit confusing and I probably didn't say it the best way, but essentially if we were to derive that, well, we get something similar to this, and yes, we would, because if we were to derive that, we get 2x, and 2x is very similar to x. But now we will use the substitution method. I will rewrite this showing we're finding the integral. Okay, now we've written this, we can move on. So, because this, if we were to derive this, it becomes this. This is what we're going to substitute. So, we're going to substitute it for a letter. I'm going to give it u. So, we'll substitute u for x squared. Now, we're going to find the derivative of this. So, derivative of u with respect to x is 2x, because the derivative of x squared is 2x. Now, I'm going to rearrange this to get dx on its own, because we have a dx on its own out here, and if we rearrange it, we might be able to do something with this and that. So I'm going to multiply the dx on top, and I'm going to divide the 2x on the bottom. So it will look something like this. And that's what we're going to be substituting, because we have a dx on its own and dx on its own, but the dx equals du over 2x. We're going to substitute du over 2x where dx is. Okay? So let's rewrite this. Capital F to show that it's the antiderivative. Little fancy S symbol, and then x sine, and we said 2x was u. We said x squared was 2, so because an x squared belongs here, a u now belongs here. And there was a dx up here, but now we know that dx also equals du over 2x. So we're going to sub in du over 2x. Now that we have that, let's work it out. Okay, 2x. We have a x over here, and because the x is multiplied to the sine, and the sine is multiplied to the du over 2x, we can eliminate these x's over here, because they're multiplied together. We have a multiplied by x and a divide by x. We also have a du multiplied to 1 over 2. So we're going to bring that out. It's going to look something like this. 1 over 2 sine u du. Because if we were to multiply the half onto du, we'd get du over 2. Anyway, because it's multiplication by a constant, we bring the constant out the front. The constant being a half, so we bring it out the front. And we focus on only finding the integral of sine u du. Now, we have 1 over 2, and we're multiplying it by whatever the integral of this is. Sine u, we know that when we derive sine, we get to cos. Then we derive cos, we get to negative sine. And we derive negative sine, we get to negative cos. And if we derive negative cos, we go back to sine. So if we were to do the reverse of that, in the antiderivative or the integral, we would go from sine to negative cos. So that's what we're going to do here. Sine goes to negative cosine. Put the u plus c. Okay, now we have our negative cos u multiplied by half, no problem. Negative half multiplied by cosine of u plus. Now, c shows we have a constant. I'm going to use a different letter, h. I used it in the other substitution video and explained why. I'll do that again. It's because we don't know what this is. We don't know if it's there or if it's not there. We just know that if we were to derive this, it would get rid of the constant. So when we integrate it, we need to put the constant. We need to put something there to show that there could have been a constant to begin with. And if we multiply half to it, it's still a constant and we still don't know what it is. But it's not the same. It's half of that. So if we put c down here, technically that is wrong because half of c doesn't equal c. We could use a new letter like I did h. H could equal half of c, but c can't equal half of c. If we weren't multiplying it by half, we would leave it just like that. But because we are multiplying this and that by a half, changing the letter shows that it's not the same. We still don't know what it is, but it's not the same as c. So I'm going to neaten this up and finish it off by drawing the capital Fx. Negative, I'll bring the cosine on top, I'll multiply it on top of the fraction, put the 2 on the bottom, plus h. And if you really wanted to, because there's a negative attached to this fraction, but there's a positive attached to the constant, you could have it h minus cosine u over 2. Now, that doesn't really do, it doesn't do anything for the equation, like mathematically wise, but simplifying it, you're getting rid of a plus sign because you don't have to show it on a, you don't generally have to show the plus sign on a positive number. So by pulling this out the front, we're getting rid of it and simplifying it, making it shorter, making it as compact as possible, and that's it. That's just a small step you can add if you want. But on that note, I'll go on to the next question that I've written up. Next example, let's say function equals sec squared x multiplied by tan x plus 1. Now, we have a function multiplied by a function, tick, and on one of the functions, if you were to derive it, you would get the outside function. Or if you were to derive one of the functions, the other function, you would end up with something that looks similar or is the other function. Hopefully that makes sense. I'm terrible at wording stuff like that. I'm sure there's not many people that are. But anyway, if we derive this, we get something similar to this or the exact same, and that's what we're going to try and find because we can. First, we rewrite it like we're finding the integral using the capital F. Find the integral on one side, find the integral on the other. Sec squared x multiplied by tan x plus 1 dx. Now, because if we derive this, we'll get something similar to this, I'll make this the u. So we go sub u in for tan x plus 1. That means the new function will look like f. X equals integral of sec squared x multiplied by u dx. So back to the u. We're going to need to find the derivative of this. Derivative of u with respect to x. Now, the derivative of tan x is sec squared of x. And the derivative of 1 is 0. So we'll plus 0, we'll leave it off. And we just are left with sec squared x. That should be in the back of your math textbook. There's probably not many, unless you're in a really low grade or a completely different type of math. That should be in the back of your textbook. But if we rearrange it as such, and we divide both sides by sec squared, and we multiply both sides by dx, we get that. Just like before, we'll sub in the dx, we'll sub in the du over sec squared. Because it equals dx, we'll sub it in for dx. Okay. I'm going to try and fit this all in. Integrals, and then we write sec squared of x multiplied by u multiplied by the derivative of u over sec squared of x. These are the exact same, and one is multiplied and one is divided, so we can get rid of them. Therefore, all we're left with now is just the integral of u du. We'll do the power rule. That'll tell us that we need to add 1 to the power. 1 plus 1 is 2, and divide by the new power, and add c. And now what we're going to do is input u. We're going to sub u back in, like what u originally was. Now we know u was tan x plus 1, so we're going to put tan x plus 1 squared over 2 plus c. And that there is our final answer to, if I can grab it, this. This here is the integral or the antiderivative of this up here. Now I hope this video helped, and I hope you have a good day, and thanks for watching.